Thank you. Thank you for this invitation. I will present the results of calculations related to the Gamow Shell model, which is a model which has been developed to study reply nuclei. It was first applied to the study of structure of unbound and halo nuclei, and then it was used in order to calculate cross sections. Then it has been used for reactions. And then I will present results related to reactions and also to halo and unbound nuclei, how we can use the Gamow Shell model for both structure and reaction applications. The scientific context is the physics of the nuclei at drip lines. Because contrary to nuclei of the valley of stability, nuclei at drip lines are open quantum systems. At the valley of stability, one has closed quantum systems because the nuclei have a large neutron proton separation energy, so that one can consider that they are disconnected from the outside world, and one can use methods based on the harmonic oscillator basis or box boundary conditions in order to describe them. It's no longer the case for open quantum systems because these nuclei can be resonance states, so that they are unstable. But even when they are bound, they can be halo states, so that they have a large coupling to the continuum. So that one can no longer consider that the nucleus is outside the rest of the world. On the contrary, it interacts with the rest of the world as can emit particles or have a coupling to the continuum. This is of course of important experimental interest because these nuclei are heavily studied in many accelerators around the world, where one tries to have access to the drip lines of the nuclear chart. For the moment, it's for light nuclei, but one hopes to go further away from the valley of stability for heavier nuclei. So that the Gamow Shell model has been developed to study these nuclei at both a structure and reaction level. The building blocks of the Gamow Shell model, it is Gamow states. Gamow states are one-body states, which can be bound, resonance, or anti-bound states. So that it's not only bound states; they can be unbound, and they are poles of the S matrix, mathematically speaking. So that they form the same object, but they have different asymptotes. Here I'm showing three types of one-body states, which are bound states, UB of R, anti-bound state, UA of R, and resonance states, US of R. UB of R is a real, UA of R is imaginary, and resonance is both real and imaginary. It is a complex state. So that it is the asymptote which tells what kinds of states one has, because a bound state will go to zero at infinity. An anti-bound state will increase exponentially with a pure exponential increase, and the resonance states will increase exponentially in modulus, but more or less rapidly according to the width or the finite lifetime of the state. So that these one-body states embody the finite life character of resonance states, and are the building blocks of the Gamow Shell model via the Bergen basis, which I will present. So that these one-body states are an extension of the bound state, because they all belong to the same class of one-body states, but they have different physical contents. This is the Bergen basis. One can see here that one is in the complex K-plane, and one can see the complex momentum associated to each one-body state, which can be resonance, anti-bound, capturing resonance, bound, and scattering. The Bergen basis is an extension of the of the so-called Newton completeness relation. The Newton completeness relation is built with bound states and scattering states of real energy. And by deforming the contour in the complex plane, one obtains the Bergen basis, where one has bound states, narrow resonance states here, and the complex contour of scattering states, so that one has a basis of complex energy states with which one can expand not only bound states, but also resonance states, which have an exponentially increasing outgoing wave function condition at infinity, so that we can consider states of a finite lifetime with the Bergen basis. In principle, one could have other kinds of Bergen basis. For example, if one encloses anti-bound states, one can have a Bergen basis with anti-bound states. It has been used in some applications, but in this application, I will not use it. I will only consider the Bergen basis based on bound narrow resonance state and scattering states. It has been shown to be very precise numerically in practice. And for this, we discretize the contour with the Gauss-Legendre production, so that we have a basis which is in the end discrete, but which converges to the continuum limit by taking more and more Gauss-Legendre points. And it has been shown that with around 30 to 50 points, we have convergence. So we arrive quickly at convergence of the continuum, even by using a quadrature, hence a discrete basis. So that the Bergen basis, in fact, is a basis with which we have both the advantages of the harmonic oscillator basis and of the Fourier transform, because as we have bound states, they are close to the harmonic oscillator basis, so that we have the structure of bound states, and on high energy, we have basically sines and cosines, so that we have the completeness properties of the Fourier transform. Hence, with the Bergen basis, we can consider nuclei which have both the one-body structure of bound states and resonance states, and also continuum coupling, because we include scattering states in the basis. So this is the one-body completeness relation. To do shell model, one needs to use a many-body completeness relation, so that we have to build the many-body completeness relation from the Bergen basis. We also have to consider the calculation of matrix elements and normalization. This is done with the complex scaling. Indeed, on the real axis, states diverge because they are unbound, so that one had to develop a new method to calculate matrix elements. And this is done with the complex scaling. Instead of going on the real axis, one goes up to a large radius outside the nucleus, and then one integrates in the complex plane. Due to the analytical properties of the one-body wave function, integrals are independent of r and theta, so that it is a well-defined method to calculate matrix elements. This doesn't work for scattering states, but this is because they have to be normalized with a Dirac delta. And this is included in the method, in quotation mark, infinite Dirac delta issuing from the normalization of scattering state is taken into account in the model, and becomes a Kronecker delta when we discretize this with the Gauss-Legendre quadrature, so that it is a well-defined method to deal with states which diverge on the real axis. It is an example of the expansion of a one-body state of a Woods-Saxon 1p3 half proton state with a basis generated by another Woods-Saxon potential. So we take a bound state here of real energy, and it is expanded with a Woods-Saxon basis where one has no bound basis states, only resonance states. We can see that here one has an overlap between the resonance and the bound state, which is very close to 1, but has a small imaginary part. And this is here the rest of the contour, which provides with components which are smaller but are important nevertheless, so that we can expand a bound state, 1p3 state, with only unbound basis states. And we could see in practical applications by calculating observables that all imaginary parts present in the expansion of the state cancel in observables because one has a bound state, so that all observables can be bound. So this shows that the Bergman basis is precise at one body level, so that we can go to the many body level. And this is how the Gamow Shell model is built. It is built with the same method as for a standard shell model. One has here our Saxon state generating bound resonance, loosely bound, and the scattering states. And by analogy with the standard shell model, one builds a basis of Slater determinants by occupying all possible one-body states. Then one has a many-body basis with which one can express the shell model Hamiltonian, but because with a basis of many-body Slater determinants, the Hamiltonian becomes a matrix to diagonalize. So that at this level, when we have a basis of generated by the by Saxon potential, the Bergman basis, and it is discretized, it becomes formally identical to standard shell model because we build Slater determinants, we calculate one body and two body matrix elements, we obtain a complex symmetric matrix, which then has to be diagonalized. It is basically the main difference between Gamow Shell model and the standard shell model, because as we have complex energy states, one obtains a complex symmetric matrix. And it has to be diagonalized. And when it is diagonalized, we have the eigenstates which correspond to physical states, which can be bound or many-body resonant states. But there is a problem which does not exist in standard shell model. It is how to identify resonances in diagonalization, because we have scattering states as well. Indeed, in standard shell model, when we diagonalize the Hamiltonian, we use the Lanchos method. And with the Lanchos method, all the low-lying states are the physical states, ground state, and then first, second excited state. But it doesn't work with the Gamow Shell model, because only the bound states are the states of lowest energy. All the resonances here are embedded in among scattering states, so that a priori we don't know how to make the difference between scattering states and resonance states. Indeed, we cannot have an exact calculation of the asymptote of many body states, so that in principle one has no way to know where the resonance is. But it is possible in practice using the overlap method. For this, we first diagonalize the Hamiltonian in pole space, which means that all the scattering states of the Bergman basis are not considered. And here we can use the Lanchos method. Then we diagonalize the Hamiltonian in full space using the Davidson method. And one identifies physical states by looking at the states which have the largest overlap with those calculated in pole space. And this way, in this example, oxygen 20, 4 neutrons above an oxygen 16 core, where only the D3 contour is considered as Bergman, because then the space is small enough to do a complete diagonalization. We can identify here the resonance states here and here. And all the rest here is made of scattering states. In order to show that with this method, the overlap method, we obtain the proper resonance states, we varied a little the D3 contour here this way by putting it a little further in the complex plane. And all scattering states here are shown to go down with the small modification of the contour, except here resonance states, which have to be independent of the contour and hence be stationary with respect to small changes of the contour, and it is the case. So this means that with the overlap method, we are able to calculate resonance states, even if we don't have access to their asymptote. We use the fact that they have a large overlap with the eigenstates obtained in the small Paul space. And we use the fact that, in fact, these states are quasi-stationary, that they are very close to bound states, to states of the Paul space, but with a small small components in the continuum, which are necessary in order for the many-body state to be well described. So that with the overlap method, we could solve this problem of identification of physical states, which would be very difficult to solve exactly, because one would have to calculate the many-body wave function in the faraway asymptotic region, which would be very difficult, especially because of the discretization of the contour, which would demand too many points. But here it's not the case. With the overlap method, we can identify resonance states properly. And of course, it also works for bound states, which can be obtained with other methods. A problem which does not exist with the harmonic oscillator basis, but which is very important with the Gamow Shell model, is how to solve center of mass excitations. With standard shell model, we can use the Lawson method, so that the fact that we have 3 degrees of freedom in the model instead of 3f-1 physically is solved by the fact that we can freeze the spurious degrees of freedom into harmonic oscillator ground state for the center of mass using the Lawson method, so that the problem has been solved for many years. But it works only with the harmonic oscillator basis. It doesn't work with the Bogwan basis, because with the Bogwan basis, we don't have the properties of the harmonic oscillator basis. So in order to deal with the center of mass excitation, we had to use another framework, and it is cluster orbital shell model, which allowed to solve this problem. For this, what we do, we no longer consider laboratory coordinates, but we consider cluster shell model coordinates here, which are the difference between laboratory coordinates and core coordinates. For this, one needs a frozen core, where one has states which are occupying, nucleons which are occupying one body states. They are frozen and they define the core. And by defining these new coefficients, these new coordinates, we have translationally invariant coordinates, so that we no longer have any center of mass excitation from the beginning, and then we don't have to correct them. From the beginning, we have a set of coordinates where which are translationally invariant, so that we can no longer have any center of mass excitation. Moreover, as these are particle coordinates, their use is identical to laboratory coordinates. We just have an additional recall term in the Hamiltonian because of these copart in the cost coordinates, so that we have a model without a center of mass excitation, and we can use it in the same way as with laboratory coordinates, because we can be slated determinants here with valence nucleons. But it is inferior to the use of Jacobi coordinates used in, for example, few body clusters, where we use Jacobi coordinates, and we can directly have a translationally invariant Hamiltonian with realistic interactions. We cannot do that because we need a core. Without a core, we cannot define the cluster orbital shell model. So that the Pauli principle is approximately treated with a Pauli operator on the core, because we only demand the one body states of the valence space to be orthogonal to those occupied in the core space. So that we have an approximate picture where the core part is decoupled from the valence part, and then we have an approximate Hamiltonian, because it has to be one body plus two body part. We cannot use Gamow shell model with a cluster orbital shell model. So that in practice, we have to define directly Hamiltonians in cos frame so that we cannot start with a realistic interaction. What we do is to have a one body part, a two body part, and we fit parameters. So that in this way, we can have an effective Hamiltonian reproducing the effect of realistic interactions. One can also, in principle, calculate effective interaction from realistic interaction in the cos coordinate, cos coordinates, but it is done at the price of a small approximation, because one has to replace a few laboratory coordinates by cos coordinates in this case, and then it is still approximate. Nevertheless, if we consider the three-body problem, we will show that the cluster orbital shell model and Jacobi coordinate models, exact models, are very close. It has been done here for the case of A6 nuclei. We took a core of helium-4 and two valence nucleons, and their ground state has been calculated using either cluster orbital shell model or the Jacobi coordinate model, standard three-body model. And we can see here that if we take a number of partial waves increasing here to 7, these one can see that these two models converge to the same value, but very slowly for Gamow shell model. GCC is a model, standard model of three-body states based on hyperspherical harmonics defined with Jacobi coordinate and solved with coupled channel. And of course, as they have a cluster built directly in the basis, it converges quickly. It is not the case with the Gamow shell model, because with the cluster orbital shell model, we have particle coordinates, not cluster coordinates, so that it converges slowly, but still it converges to the same value, and with L equal 10, typically we have convergence. So that the cluster orbital shell model can be used for both bound states here and also resonant states. And we can see here that states are very close in energy. So this means that the cluster orbital shell model can be used safely, like with Jacobi coordinates, but one has to pay attention that a small part of the remaining space is renormalized in Hamiltonian parameters. And it is the main limitation, in fact, of the cluster orbital shell model. The Hamiltonian is effective. Nevertheless, we have good results, and we can consider that the cluster orbital shell model gives very close results, very close to exact, and can be used without problems. We fitted here a Hamiltonian, effective Hamiltonian, with the cluster orbital shell model for light nuclei with a helium-4 core going from helium-5 to lithium-9. And we can see here that experimental data are really produced. These are given by stars for both unbound and bound states. And then we could devise a Hamiltonian which can describe light nuclei. So the structure of the interaction, which is the Futani-Tamagaki or FHT interaction, is standard. It has a central tensor spin-orbit parts. So this is very common in two-body interactions. And there is a one-body part, Woods-Saxon part for the effect of the core. What is new compared to the fit of all the interactions is that we did a statistical analysis of parameters. It can be seen here. This is the fitted value of parameters, and it is the error calculated with here linear regression. And we can see here that we have two kinds of parameters. Well-fitted parameters here, where the error is much smaller than the value of the parameter, and here slopy parameters, where the error is much larger than the fitted value, which means that they don't have a large effect on the energy of fitted many body states. This means that one has to pay attention when you fit an interaction, and it cannot be seen without any statistical analysis. One has to pay attention that some parameters are well constrained, while others are basically not constrained at all. So that when we fit interaction, it's better to mainly fit these kinds of parameters here, which are well constrained, and this one can be neglected. For example, in some applications, if we see that they have too large uncertainties. It is done with linear regression, but we plan to use Bayesian statistical analysis in future because errors are more significant when using Bayesian analysis. Nevertheless, with linear regression, one could see that we could identify well-constrained and sloppy parameters. And we could see that we have an effective interaction which can be used in practice in order to calculate the structure and the reaction properties of nuclei close to nuclei. This is another application, a recent application of the reflection interaction with the helium-4 core. It has been considered for lithium isotopes and their mirrors. And we can see here that we have a very good description of experimental data. Here, the difference is that we use an SP space, no D partial wave, because it was too large. Nevertheless, we could have good results. And also, as I said before, we could use we could use renormalization of the interaction by neglecting parameters which are not important, and this could be done using effective theory arguments. We can see here that one could calculate two kinds of states, the lithium isotopes and their mirrors, which are proton-rich and which are broad resonances. Then we can see that we have a strong Thomas-Hellman shift because, as we can see here, the states are very different. The spectrum is very different when going from neutron-rich to proton-rich. So that by using fit on the given experimentally known states and going to the drip line, both neutron and neutron, we can identify how the Coulomb interaction modifies the structure of states, because it is well known that the Coulomb interaction generates a strong Thomas-Hellman shift in resonance states. Moreover, the proton-rich nuclei are not well known experimentally. For example, nitrogen 10 and oxygen 11 are being studied experimentally and theoretically, but they are not. There are not many data, so that the Gamow Shell model can help determine their structure. And for the moment, we have seen that it is consistent with recent analysis, so that this shows that the Gamow Shell model can be used to study nuclei at drip line where continuum coupling is very large. I will present two examples of a structure at drip line before going to reactions. Here we could see that by fitting the fluorine chain, we could get a 2-neutron halo in fluorine 31, which is the last known isotope of the fluorine chain. And it has been suspected to be a 2-neutron halo. And then in order to see theoretically if it is how it behaves, we fitted the fluorine isotopes, and then we could obtain a 2-neutron halo here, which can be seen from both two correlation density and neutron density. Indeed, if we have a halo, a 2-neutron halo, it has to be seen not only in density but also correlation density, because the two nucleons have to be in the halo and not just one. And it is the case, as we can see here, because fluorine 31, its correlation density decreases slower than those of the more bound fluorine 27 and fluorine 29. So that with the Gamow Shell model, we could confirm that at a theoretical point of view, fluorine 31 is a 2-neutron halo nucleus and maybe the heaviest 2-neutron halo synthesized experimentally. Conversely, we studied the proton-rich nucleus, neon 17, because it is suspected to be a two-proton halo. And here it is the same. We could devise a model where it is a two-proton halo state. Moreover, we used here realistic Hamiltonian. We normalized in order to be used with an oxygen 14 core, an halo interaction calculated with the EKK method, and in an SDP space as before. And also we could investigate the effect of three-body forces. And what was interesting in this model is that we could see that the three-body force does not influence the halo property of neon 17. It only changes energy. Whereas the continuum coupling is very important for this, as can be seen here. Here it is done calculation with continuum, and here without continuum. And we can see that even though here we include three-body forces, but no continuum, we don't have any halo, and here's the opposite. With or without three nucleon forces, we have a halo. This means that in order to produce a halo, it is continuum coupling which is the most important. The three nucleon forces are, are important only for energy, but not for asymptotic properties. These were structure calculations. A useful tool for reactions is the asymptotic normalization coefficient, which is the way the overlap function behaves in the asymptotic region. And it is important from an experimental point of view because cross sections of low energy are proportional to the square of the INC, so that this quantity, which can be calculated in Shell model, can give access to cross sections. So that they have been calculated for nuclei of a few nucleons, well, with a helium-4 core, and we used here a phenomenological interaction in order to have an interaction which is easy to fit, because we wanted to consider mainly the behavior of the overlap function in the asymptotic region, and then calculate precisely asymptotic normalization coefficient. This is of important interest from astrophysics because there are several processes of astrophysical interest which can be related to these cross sections, such as solar neutrinos or opposite lithium abundance, which will be mentioned also in
Sorry, it looks like something happened to Nicolas' connection. Let's see if we can solve this. Sorry, I will try to see what's going on. So it looks like he got disconnected, so we will try to have him back and continue with the seminar. Sorry for this.
Okay.
Hi, are you back?
Yes. Yeah, everyone has to share screen.
Yes.
Think it is okay now?
Yes, it looks
Okay.
fine. Yes.
Okay.
Can you go full screen?
Yes. So here, these are overlap functions calculated with the Gamow Shell model by fitting a Hamiltonian for the A equals 6, 7 nuclei, beryllium 7, lithium 7, and lithium 6. And from these overlap functions, we calculate the INC by fitting the overlap function with the Hankel or Coulomb function times ANC. The Hankel or Coulomb function is directly calculated from the separation energy between the two nuclei, so that the ANC is obtained by fitting this Hankel or Coulomb function times ANC, and we can see that here in the asymptotic region, it is an almost exact reproduction of the overlap function, which means that with the Gamow Shell model, we can calculate precisely ANC with the overlap function issued from a structure calculation. Here, one has a recoupling to the continuum because all states here are well bounded. These are the ground states of these states. So that is interesting to see if it also works with loosely bound resonance states, which has been done. Here we considered beryllium 7 boron 8 nuclei, as well as lithium 7, lithium 8. It is interesting because boron 8 is a 1 proton halo. And we can see here the effect of the 1 proton halo because the overlap function decreases slowly, much slower than the more bound lithium 8. So that this means that we can also calculate the overlap functions related to the halo structure of a given nucleus. And here as well, we have a good description of the overlap function in the asymptotic region with a Hankel or Coulomb function. And then we can calculate ANC precisely as well for loosely bound states. And here it is an example with unbound states. Because as we use the Gamow Shell model, where we have complex energies and resonance states are analytic continuation of bound states, this method of fitting the ANC with overlap function should also work in the complex plane, and it does. Because here one can see that the 3+ excited state, which has a large width, is also well described in the asymptotic region with complex ANC times the Coulomb function. And it is the same here with Hankel function times complex ANC. This means that we can calculate also a complex ANC associated to resonance states, so that with the Gamow Shell model, we can calculate ANC not only of bound states, but also of resonance states. And for example, calculate widths with these states, which has also been done and provides basically the same weights as that given with the diagonalization of the Hamiltonian. It has been checked for these nuclei, and we could see that results are consistent. So that with the Gamow Shell model, we have access to the asymptote of given by the overlap function, even though in practice it would be very difficult to fix the asymptote of a many-body state from the beginning, especially because we discretize the contour, so that it would be too difficult to have an exact many-body asymptote. But with the overlap function, we can have access to the ANC and fit it with Hankel or Coulomb function times the ANC, so that it is a precise way to consider the asymptote of many-body wave functions and also calculate observables depending directly on ANC. This was, for the moment, only structure calculations. Even though ANC can be directly related to cross-sections, we have not calculated the cross-section yet for the moment. But it has been done, and it has been applied to several calculations, as we will see. One could think that with the Gamow Shell model, we would just have to diagonalize the Hamiltonian and consider scattering states, many body scattering states, and then calculate phase shifts, cross sections from them. But it is not possible because we don't know the asymptotic behavior of these states. They can have one particle, two particles, three particles in the continuum. We don't know. And then the scattering eigenstates given by a direct diagonalization of the Hamiltonian would be too complicated to use to get cross sections. So that we prefer to develop another theoretical framework. It is based on the resonating group method. In this standard method, we built channels from target and projectile states. Target states are given from the Gamow Shell model because they are bound or resonant states. Then with projectile states, we built channels, and then we have a couple channels equation to solve, and then what we call GSMCC, which is a couple channel Gamow Shell model where one has a basis of channels built from target and projectile states, and from where one can calculate scattering states with a fixed asymptote, one nucleon, two nucleon cluster, so that we can calculate phase shifts and cross sections precisely. The idea is to have the same Hamiltonian in Gamow Shell model and in the resonating group method, because then one has unification of structure reactions. But yeah, for the moment, it's still not possible, so that we have to fine-tune Hamiltonian parameters in order to calculate cross sections which are close to experimental data. But it is the aim of GSMCC to have a unique Hamiltonian with which both structure and reaction observables are calculated. We can calculate cross sections of proton-neutron, scattering radiative capture. Now also of clusters such as neutron. We have done calculations of scattering reactions. Now transfer can be done. I will show the first calculations of neutron transfer reactions. Radiative capture is in progress. In principle, we can consider projectiles of helium-4, triton, helium-3, but tests are in progress because its calculations are more difficult from a practical point of view with many body clusters, even though the method is coded and we can do calculations, but it demands testing because it's more difficult than with proton and neutron in practice. Applications concern direct and transfer reactions of low energy of astrophysical interest. And we considered elastic and inelastic scattering reactions, as well as proton and neutron radiative capture. Will show results now. This was the first calculation that we did with GSMCC, which is proton on neon 18. It is excitation functions proton-proton neon 18. And we calculated excitation functions at large angles, as you can see here, and the data are very well reproduced. But this is because neon 19 are very narrow unbound states with small continuum coupling, so that it was not so difficult in this case to have a good model with only an oxygen 16 core and a PSD Bergen space. We used also phenomenological interactions of Gaussian. But only by having a good spectrum of neon 19 and using the RGM, we could have very good excitation functions. So this means that here the energetics of neon 19 are the most prominent to have a good description of cross sections. Here, continuum coupling is not important. Nevertheless, it showed that we have a practical method to calculate cross sections with GSMCC. This is a more complicated application, which has been done a few years ago, and it is related to the resonances of fluorine 15. It is proton-proton on oxygen 14, and fluorine 15 is basically one proton above oxygen 14, so that its two first states are basically single particle states, 1/2 plus, 5/2 plus, very close to 1s 1/2 and 0d 5/2. But what was seen experimentally and could not be explained is the appearance of a narrow 1/2 minor states here above the Coulomb barrier, but with a very small width, about 30 keV. And one could not explain it. And in order to explain it, Gamow Shell model calculations have been done. And it has been seen that at structure level, the state has a lot of components with 2s1/2 in the continuum, so that we could interpret its small width by the fact that it has only a small phase space available for decay. So that its small width was explained by its structure, where the state, even though is above the Coulomb barrier, cannot decay because it doesn't have enough configuration space for it. And then this appearance of a narrow 1/2 minor state could be explained from a structure level, but also from a reaction level, because its effect on the cross-section here could be reproduced with GSM-CC. You could see here the I matrix fit. Here it is the best fit. Here it is a fit where the ground state has a fixed width. And we can see that all these calculations are very close. So that this means that the Gamow Shell model can help solve problems, answer questions which can occur at an experimental level. And the model space was also very simple. Valence protons above the carbon 12 core, so only three valence protons. We just need a small valence space in order to have a good physical description of the structure and reaction related to this scattering reaction involving the dripline nucleus fluorine 15. This is an example of radiative capture, where a boronate is very important because it's what is created when having a radiative capture of proton on beryllium-7. It is of astrophysical interest because it's related to the solar neutrino flux in the sun, where the most energetic neutrinos are created by this reaction proton on beryllium-7 in the sun. So that the calculation of radiative capture cross-section in this case is of important astrophysical interest. And it has been done for P gamma and gamma on beryllium-7, lithium-7, and we can see that experimental data are well described. And we also did two calculations. A solid line is a full calculation, and dashed line is a calculation where we don't consider the first excited state as target state. And we see that there is a significant difference between the two, so that we need several target states, not only the ground state, in order to have a full calculation. And we can see that at low energy, P gamma is very well described, not so much at higher energy, but qualitatively, as we have also a simple many body wave function, valence nucleus above helium-4 core, it is satisfactory. And we also have a good N gamma cross-section. So this means that we can calculate a radiative capture cross-section with the Gamow Shell model and compare also cross-sections and the structure, because we can calculate as well the many body states with Gamow Shell model. We also calculated the astrophysical factor at zero energy, and we can see that it is very close to experimental data. This is also radiative capture, but on lithium-6, P gamma and gamma. It's related to the puzzle abundance of lithium-6-7, where the theoretical estimates and the experimental measurements don't match when we consider the abundance of lithium-6 and 7. And then the study of radiative capture in cross-section in this case is of astrophysical interest. And we can see here that we have a good description overall of the cross-section P gamma as well as N gamma here, even though there is a small discrepancy at higher energy. But the space is the same as before. Valence nucleus above helium-4 core. It's a very small space. Also, the FH interaction has been used and fitted in this case. And we can see here that we can have good agreement with experimental data, so that for this complicated theoretical problem, the Gamow Shell model can be used as well, and we hope that it will help give information about this problem of puzzled abundances of lithium in the universe. I will finish with the first calculations with the many-body cluster, hence with the deuteron cluster. Here we calculated the scattering deuteron-neutron on helium-4. The model is very close to that used before, valence nucleons above an alpha core. The difference is that we have a deuteron, and it is calculated differently and needed, in fact, another approximation. Because what we tried first is to fit the structure of lithium-6 as before, but it, as we will see, results was not so good. So that's what we did. We fitted instead the ANC of lithium-6, so that the one state is to bound. But we will see in the cross sections that in fact it's better to fit ANC and not energy, because cross sections are better reproduced. One can see here, here it's a spectrum which is fitted. Here it is the ANC which is fitted, and we can see that by fitting the ANC, one is closer to experimental data. Added to that, the deuteron structure is calculated from a realistic interaction, from n3LO interaction. This bracket is included because we have scattering deuteron states, because we use a Bogon basis of deuteron states in the deuteron expansion. But we still have a Heffecht interaction between valence nucleons, because this means that deuteron is scattering in the asymptotic region, but in the close to the target. We use Gamow Shell model, and we have the Heffecht interaction. So we have two different interactions for the moment. Nevertheless, we can have a good description of experimental data, especially with the ANC fit. Here it is higher energy. One can see that it is more difficult to have a good description of cross sections at higher energy, especially with the spectrum fit, which is not the best as we saw, but also with the ANC fit, where, for example, here we cannot have the minima at the right place. We think that it is due to the fact that we don't use three-body forces, because these cross sections can be very well described in a no-core picture. But in our case, even we have a small space, and then we don't have as realistic a Hamiltonian as with no core. Nevertheless, we have what a good description of experimental data, considering the simplicity of the approach. And it is the idea of the Gamow Shell model GSMCC used with the core. It is not as precise as a no-core shell model, but it can be used with more nuclei, because with the core, we just need a few valence nucleons for heavy, medium or heavy nuclei. And then we can have not so expensive calculations, which cannot be done with a no-core shell model. So that it is a trade-off between numerical cost and the realistic character of the used Hamiltonian, which is, yes, more effective in our case. So we'll finish with the first calculations of DP reaction, which has been done also in a simple space, calcium-40, a core calcium-40 with deuteron, and hence two valence nucleons above a core. Calcium-40 is not so good a core, so we can just consider deuteron of low energy. Here we took a 1.9 MeV, which is smaller than the first excited state of calcium-40, so that we could expect to have good results. We could nevertheless fit a good proton and neutron scattering cross sections on calcium-40, and we can see that they are well described, except here at the very end of neutron scattering, which would increase, but it decreases instead. But at large energy, it's very difficult to have a good cross-section with a simple model where the nuclear interaction is too simple. And here, most importantly, we can see that the DP cross-section is very well described up to 120 degrees, even though we have a very small space, a very simple interaction, which is as before, FHT interaction, calcium a core, here calcium 40, and a deuteron, which is generated by a N3LO interaction. We don't have breakup also in this case because it's very simple, and it is at low energy. Nevertheless, we can have a good result. And for a first calculation of a DP cross-section, we can be satisfied with this calculation because here one can see that we are very close to experimental data. Nevertheless, internucleon correlations are missing. And in the future, if we want to consider DP reaction, we have to include more correlations by having a larger space. We published a book about the Gamow Shell model about 1 month ago. It's called the Gamow Shell Model Unified Theory of Nuclear Structure and Reactions. So most of the results that you have seen in this presentation are described there. The background is that of university, functional analysis, linear algebra, differential equations, and the whole theory of the Gamow Shell model is presented for both structure and reactions, and also more systems, one body, two body systems, halos and resonance in nuclei, but also molecules, examples of structure and reactions, and also exercises. And the code is available on internet, with which one can redo the calculations shown in this book. So it is available at Springer and can be bought on internet easily. Then as a conclusion, we have the Gamow Shell model, two main models. Gamow Shell model for structure and GSMCC Gamow Shell model for reactions. And they are complementary because GSM includes continuum in a structure model, whereas GSMCC includes structure in a reaction model because targets are calculated with a shell model approach. We could calculate structure and reaction observables. We have an effective interaction for light nuclei. We calculated ANC with which are observables dependent on spectrum, as we saw. And also we could identify the halo structure of two nuclei adduct lines, which are heavily studied experimentally. From a reaction point of view, we can consider elastic, inelastic, scattering cross-section, radiative capture cross-sections, and also many body projectiles with the example of deuteron projectile calculated for scattering and transfer reactions. Still, we need to fine-tune Hamiltonian parameters, but we hope that soon we could get an approach where a single Hamiltonian can describe both structure in reaction. And we published a book on Gamow Shell model and GSMCC, which is available and where one has a lot of applications which can be done there. Codes can be run, theories explained, and there are also many exercises to better understand GSM and GSMCC. In the future, we plan to use GSM with many isotopic chains with effective and realistic interactions. Indeed, we have the FHT interaction, which has to be fitted, but also we can calculate realistic framework with the core using the AKK method, as I showed with the Neon 17. With GSMCC, we plan to consider more calculations with few nucleon clusters, deuteron, but also triton, and maybe alpha soon. We could consider also the effect of non-resonant channels, because for the moment you can only include resonant targets, but we saw that in some applications it's not sufficient, so it can be studied. And also we would like to calculate theoretical uncertainties of the fitted parameters with Bayesian statistics, especially for the FHT interaction. Thank you.